let's kickstart today's seminar, and it's as part of the SSSSS series, the special seminar series on survey and space mission. Today we have great honor and pleasure to have Professor Kinwah, who is a chair professor in theoretical astrophysics at University College London, joining us. Professor Wu did his undergraduate study in physics and mathematics at Chinese University of Hong Kong, and received his PhD from Louisiana State University. After his position at Australian National University, NASA Marshall Space Flight Centre, and University of Sydney, he then moved to UK, joining University College London, Malast Space Science Laboratory, MSSL-UCL. First as a reader, and later he got appointed as the chair professor in theoretical astrophysics and was the former MSSL head of theory. Professor Wu also held honorary professorship at University of Hong Kong, University of Sydney, Macquarie University, and as a guest chair at Nanjing University. He also received a very prestigious award, UK Royal Society Ken Tompo Professorship in 2008 and 2009, and also the New South Wales State Expatriate Research Award in 2006. I was super lucky to have met Professor Wu when I was still an undergraduate student at Oxford, making an appointment to see him at University of Hong Kong, actually. And then later he brought me to astrophysics, and I learned a lot from him. Professor Wu's research area, I would say it covers a wide range, from polarized radioactive processes and radioactive transfer, instabilities in magnetic shocks, accretion and outflow, general relativistic radioactive transfer, covariant transport of photonic and non-photonic particles, hadronic interaction in galactic and intergalactic environment, general relativistic and high energy processes in extreme mass ratio system, and multi-messenger astrophysics. I also know he also do biophysics research and have that interest as well. So it's great to have him here today. And this talk, he will particularly talk about how to resolve fundamental physics and astrophysics problem using multi-messenger signals from extreme mass ratio and intermediate mass ratio binaries containing a millisecond pulsar. So over to you, Professor Wu.
Okay, so I have to share screen. Okay, do you see my screen?
Yes.
Okay, thank you very much for the invitation. The title of the talk is a little bit long, so it looked like an observational title, but most of the work actually is about what we perceive the observation, in which direction that we can do this. So the key ingredient are the extreme mass ratio system and the multi-messenger signal. So this is, I mean, a long, ongoing project for many years. Mostly I will work with summer students, undergraduate students. So, and some of them, I mean, eventually become my PhD student. And also, I mean, a few colleagues who is happy, I mean, to use their spare time to help me out if I need. So my the contribution in this today, I mean, involved in some of them. So here is the list. So the outline, I mean, I will talk about gravitational wave astronomy, extreme mass ratio system. And then, I mean, I will talk about some issues in astrophysics and fundamental physics. And then, I mean, the apparatus for us for the investigation is the spinning object around massive black hole. And why do we use this, and what is the advantage of this? And it's quite interesting, and also it's unique. And then I picked one case that currently I'm working on myself, and also, I mean, my current PhD student also joined us. She is a very intelligent student. She started university at 14 years old. So no, okay. So let's, I mean, start with something, I mean, everybody is familiar with, but also means very important. Now we start with, I mean, the gravitational wave astronomy extreme mass ratio. So this one, I mean, is not usually when we talk about emerging black hole. But I picked the system, I mean, it's particularly important, actually, is the emerging neutron star. Why is it important? Because, I mean, we have the electromagnetic counterpart. So we do not rely on gravitational wave, but we truly make gravitational wave astronomy part of the multi-messenger astronomy. Secondly, I mean, we can identify this system with a gamma ray burst. So we confirm that it's an emerging neutron star. So black hole is fascinating, but neutron star is a harder subject. The good thing about neutron star is that even though when it is isolated, we can see it. It's unlike black hole. Black hole, we need to require on something around. So that makes, this kind of system is very unique. Now, when you see here, you see, the gamma ray burst, but also, you see the gravitational wave finally in spiral. There's a time difference. But before that, there already something happened. The time between here, if I remember correctly, is about 2 seconds. I think about 4 seconds, there's something here, but not in this source, but in the other sources. And we can actually model it. So this, the work, I work with some of my mentees. One of them is my mentee. Actually, so this one, is another gamma ray burst. So it is a 4 second before 4 seconds, there's something here. So what I mean is that, before, the gamma ray truly the breakout and in spiral, if we assume the time scale is more or less the same, then it means that the two neutrons start begin to interact. So what I mean is that there are some electromagnetic radiation. In fact, actually we pick up the X-ray data. Actually, we can model. We can model it quite nicely. We can have, like for example, a magnetic interaction model. We can devise the spectrum that can fit quite nicely. So why is it important? It's because when there's some kind of system, there's a black hole. If there are two black holes, we have to wait until the gravitational wave. But if there's one neutron star, we always can see something. And the neutron star, sometimes we cannot see it because we are incapable to do it because of instrumentation or because the source is too far away. But theoretically, nothing can stop us to see it. So one of the systems which is particularly useful is the extreme mass laser binary system. Now, if they are similar mass, not because they are not interesting, but it's difficult to handle theoretically. So we pick the one that we can do some reasonable approximation and get some useful information. So this is the system that I'm interested in. So basically, we want a very, very fast spinning neutron star and a black hole. And the black hole is also spinning. The other one I'm interested in is two neutron stars and a black hole. So what's the difference between this? This is a hierarchy triple system. And there are more interesting things from a hierarchy triple apart from. So in this case, we dump a binary system in a gravitational field provided mostly by the black hole. So we study another aspect of the system. So these are the two kind of systems mostly we talk about in this talk. So are these systems detectable? Yes. So if you look at this in the frequency range, they are here. And this is in spiral. But before in spiral, they are longer frequency. It means that now they are moved further into here. It means that the chance to discover it is much, much better. So why is this system unique? So it relates to our understanding of physics. Our understanding of physics eventually come down. How good is we get a clock and how good we get a ruler? So let's look at the ruler first. To get this, what we mean that we need to have a measurement with a precision about 1 part in 10 to the 21. If we want to study very important physics in general, to the high order effect. So what does it mean? Now, if you look out for LIGO, what it means that we need to look at some kind of length scale smaller than a proton with the arm length of the LIGO, which is 4 kilometers. Now, if you translate into an astronomy perspective, what it means that we need to resolve a thickness smaller than a human hair from the closest star to us. It's Proxima Centauri, is about 4 light years. And this means the one is on the task of gravitational wave. But on here, don't forget about in another astronomy, we actually had a very, very good clock. That's the radio pulsar timing. Now, radio pulsar timing is slightly tricky. It is not just about picking one pulse and you get accuracy. You need to sum over many, many pulses. Well, I think it's a 10 to 4, 10 to 5, and then you get something. So, but at least it means achievable. But the stability of the millisecond pulsar is important. It means that we can trust the clock, even though we cannot do our experiment properly. But the clock has no problem. It is just we have problem. But we get problem, we can improve. The clock has problem, then we cannot do anything. So this, we keep it in mind. We get the gravitational wave, and also we get the pulsar. So the fast spinning neutron star around a black hole basically is a combine the high precision independently, one from the pulsar measurement, the other one from gravitational wave. So it means that now we can do a foot trap method or whatever, to calibrate cross calibration, or there's a systematic bias And we are not unlucky to a point that the systematic bias is the same for both experiment and observation. So let's talk about some issues we want to tackle. So let's look at the astronomy. So there are certain kind of things, okay, we want to check the pulsar in close orbit around a massive black hole. Now, we in a theoretical perspective, in observational perspective, of course, there are many things that we cannot control because we just sit there and put our telescope there. But theoretically, it means that is the possibility. Is there any impossible thing? The second thing is, hierarchy system in planetary system is already give us a headache. How about, what happens in a strong gravity? Will there be any additional thing that we need to consider? Now let's do something more familiar to all of us, that at least it is doable in other areas. Like for example, is the M galaxy relation. One of them is the M sigma relation. We universally hold even down to the low mass galaxy and the stellar spheroid, such as in the spiral galaxy or in the Goblet cluster. Now, for it to hold, it means that you need to be present in the intermediate nuclear mass black hole. Now, finding the intermediate mass black hole is not so easy. So even now, some your people think that not that evident that they are actually neutron star. So to nail down the intermediate mass nuclear black hole in low mass dwarf galaxy is very important. So, and then of course, how can we measure the mass and the spin of the black hole accurately? So you look at the M sigma relation. It's very nicely. But you look at that, it mostly stop at 10 to the 6. So if you further push it, 10 to the 5, it means that it's really difficult to measure the mass here. And then there's a question: will the whole thing actually hold, or there's another one, or there's a deviation? Now the relation of this depend on the scatter of this. It means that it also depend on the accuracy of your measurement. If you do not get accuracy, it means that but if you have a very few sources apart from doing the Poisson statistic, then it's what's the accuracy of the measurement. If you measure the source very accurately, then you reduce the error bar. It means that you increase the statistical weight. So it means that we need one or two very good system. But unfortunately, the accuracy to measure the mass of the black hole increase if the black hole mass is very small in using stellar dynamics. So this is the question we need to deal with. Then go back to physics. And what are the things actually we concern? So of course, then in a practical physics, is how the particle wave propagate dynamical space-time. Among the audience here, actually, is this something that she was a student with me. So this is the problem. And then the other one is how is the spinning of the interact with the space-time curvature macroscopically and microscopically. So this is the first level. Now in the more immediate level, we need to deal with is how to correct the self-force effect in gravitational wave observation. Now this one is particularly important because a lot of the people in the LISA team actually need to deal with this problem. If we have problem, we deal with this problem. A lot of the LISA's observation will not be successfully performed. So this means the problem we need to solve before LISA is launched. Now, then further down, they are more philosophical. Is how to measure the gravitational clock effect. Usually, people use satellite around the Earth to do this, but we have a better means to do it. And also, this effect, actually, we can make use of a better clock that provided by nature. And then there are something even more fundamental: is what is the nature of gravitational wave memory? Actually, gravitational wave pass through the space-time to leave a memory. So this is something like similar to nonlinear optics. If the photon pass through optical fiber, it will change the optical fiber. So the part of photon and the behavior of part of photon and the photon behind is completely different. And finally, philosophically, what is time? So this is the question that I'm interested in, and I try to think of some way in astrophysics to deal with this question. So let's look at the mass. The mass is not well defined in generative and also in relativity. So because the mass is according to the thing move faster, you get more mass. So if you have an observer here moving, the object is spinning. So you find that actually different observer actually find a different center of mass is different. Now that become complicated. It means that now we cannot define what is center of mass. A lot of the observation of the physics, we use the center of mass as approximation. Secondly, there's another big problem. because in the Einstein's equation, it talk about energy density, it never talk about mass. It's unlike in the Newton description. So what it means is that we need to do integration. What it means is that we need a surface, but defining a surface is very, very difficult because it means that you need to fix the time. But everybody at a different time. So how do we get the mass? So if we do not get a mass, then now there is a problem because in all the so-called the dynamical system there, and then we have the so-called concept of world line, geodesic. All this is a point mass approximation. If we have problem to define this, and then there is a problem. Now, if I put into the spin, now there is a problem. So this is the, if you have a spin, then it means that it does not follow even a geodesic. So if there's a spinning object, so the world line concept does not work because there's no center of mass. And then we have to introduce a concept for world 2. But we solve the problem, not necessary, but it just introduces more problem. So now we go back to another problem, is the gravitational member. This is my student when she was doing undergraduate. So then she calculated the gravitational wave pass through. Then you have 2 different modes, the cross mode and the plus mode. The cross mode actually you can see the whole thing actually change. So it means that when you reverse the time, you cannot get the same thing. So this is the gravitational member. And the Spin-curvature actually can bring something new as well. So the other thing is when you look at this diagram, you see this diagram many times. If you examine this very carefully, you find there is something popping out. It is not because the artist is not good enough painting it wrongly, but it means something. What I mean is that this small guy actually distort the gravitational well of this. Now, then it means that now this whole system need to move in a joint gravitational. Now, this thing is not linear. So this means one type of back reaction, and then we need to do. So next, we need to talk about what are we going to do. So the key is a spinning object around the black hole. So this one, actually, neutron star is one type of spinning object. So in astrophysics, naturally, we choose the neutron star around a black hole. Now, black hole around black hole also work, but the problem is that we cannot have a clock. So what does it mean? Let's translate the abstract concept. Basically, we put a gyro in a curved space-time. So if you play around with the gyro, it's the top, then on the floor, you see a lot of interesting behavior, like jumping around. Sometimes it's chaotic, sometimes it's very stable. It's the same thing. If you put in curved space-time, it also like this. Now the gyro interact with the floor, but this gyro interact with the 4-dimensional curved space-time. So if you put a millisecond pulsar now, it becomes important because this gyro carry a clock. So now we have 2 clocks. The clock belongs to this pulsar, and the clock belongs to us. And so when you have 2 clocks, we can do a lot of things in typical. Now, before we get into this, let's some revision of classical E&M. So we have the 4 Maxwell equation. Now you see in CGS unit, astronomers like to use CGS unit, undergraduate students like to use SR. So I put it in CGS unit. So we have the 4 equations, and these are the whole package of E&M derived from this set of equations. But in relativity, if we linearize the Einstein equation, we also get a set of equations. So it is very similar to the Maxwell equation. But you find something is very strange. You find a lot of 2 there. The 2 is because of the magnetic field is spin 2, the EM field is spin 1. So this means the simplest holistic description. And also the charge of the point particle actually is some of the 2 and some the. So we get the same equation. So it means that we have the gravitoelectric field, and also we have the gravitomagnetic field. So now it becomes handy. It means that we do not need to start from scratch. We just make use of it. We linearize whatever the equation of motion and express terms in this. The question is, can we do this in this kind of system? Actually, yes. Now, so let's try with this one. So this one basically, okay. Now, why to choose this one? This one is more interesting. So you have 2 systems. So it means that now you are moving mass. So in E&M, you have when we have moving charge, then we have current. So it means that now we have an equivalent mass current of this system. So it means that not just we can talk about something very abstract like spin interaction, but now we can talk about the current interaction. And so it means that now we can take advantage of the whole magnetism with the presence of current. So before that, we need to do some algebra. So let's start with the same thing. So if, the same thing in general relativity. So if you have two particles orbiting around free fall, so the whole in the black hole's gravity. So basically, the whole thing experienced by the two particles is the tidal force because they are in different position in the space-time provided by the black hole. So there's a tidal force. So after we do all this kind of algebra in the first approximation, more or less, we get this group equation. Now this is not quite transparency, but on hand we look examine something like this. Now so this one is a coordinate, it's like x the time, and this R3 is the tidal force. Okay, so it's a GM. So this is a typical tidal force type equation. So after that, of course, we do all kind of combination about the movement or all this, and eventually, we combine, some potential term. We find something is very interesting. So it depends on the S, it means that the orbital angular momentum of the two neutron stars and the big orbital angular momentum of the binary around the black hole. So this is quite similar to what we learned in atomic physics as well. So that's is what we have the Spin-curvature effect and the Siemens splitting atomic physics. We learned this before. So the configuration of the system is like this. Now the electron had a kind of magnetic moment. Now we imagine that thing is generated by some kind of current. Actually, it's not. And then now there is around an atom there is L, so we get the SL coupling. So in this case, you find there is a splitting of the energy of this kind of coupling. Okay. After we do all this, we write down everything in Euler angle. We can write down the Lagrangian. So actually, in the linear decomposition, actually we can identify each term quite easily. So here, the SL coupling term, we have the tidal term, we have the centrifugal force and the Coriolis force and the rotation. So, but if you look at this Lagrangian, then we find the potential actually very strange. In some direction, actually, it's elliptical. In some direction, it's hyperbolic. So this kind of system guaranteed chaos. So let's look at the system. So you look at the notation and precession of the normal vector. That now we compare with the Newtonian. So it behaves differently. So we can see actually the spin curvature coupling actually came in. Now Newtonian system also presets and notate. We learned it in classical mechanics already. But you look at the phase space analysis, we just plot the whole thing about the theta phi. So sometimes we find that it is just a scatter in the theta phi plane, and sometimes we just wandering around randomly. So this one is basically means like a chaotic system. Now the most important thing, interesting thing actually is this. So it had a phase lock, and then you lock them in this scatter. So each of them actually is one cycle, one phase cycle. So after a while, it suddenly unlocked itself, and then it becomes chaotic motion, and then it's normalized again. So this is very similar to the analog so we can use a electric circuit to do this. If you look at it previously, go back here. All these are sine cosine functions, so we can build electronic instrument actually to simulate this. Now that one is we express the whole thing in the electromagnetic interaction. But more precisely, what happens if we want to properly the electromagnetic decomposition is a low order decomposition. If we want to continue to a high order decomposition in the model expansion, actually we can write in the MPD formalism. So when you look at that, you get the so-called induction term. This is the spin, is the velocity, is the Riemann curvature tensor. Now you have the anti-symmetry term. So it's the spin, it's a typical thing classically. So for the force, this this thing. Now this one must be a torque. So this one must be a force. The whole thing is generalized. If it is, in the momentum term is a force. So then we can have the Dixon force and the Dixon torque. Now But this equation actually is a moment equation. It means that it cannot be closed. There are more variable than the equation provides. So we need to introduce a closed condition. One of the closed conditions is called the supplementary, the Dixon spin supplementary condition. Now, of course, there are alternatives. Now, so this one actually you need to project on the momentum, and this one is projected on the velocity. Now, but there are differences because because it's a spinning object, so the momentum is not even the mass. We keep it as a constant, then not necessary. But the worst is that the mass you cannot have this relation if it's a spinning object. But on hand, this thing vanish and the self force it's not there. This time will go away. Then eventually we get the two condition reconciled. But this is a problem because if you look at the and this is the problem because now it depends on the shift. So the center of mass now, what are we going to do? Which condition to use? So this is the issue. Now, of course, if you get into the higher order quadruple term, then we need to do the higher order quadruple expansion. So it's not now. It is not low order point dipole interaction, but also the quadruple order. So this is the recent paper that we accepted is going to publish very soon. I think probably a few weeks ago. So this is how we got. So now let's do a demo. So why is this thing is important? How we can use it? And this is the question we want to ask. So we can write down the MPD equation. We can reduce it to a form which is more pleasant. Now, if you look at that, this one basically is like Newton's law. It's a change of momentum by the of time in the form momentum. So the first one actually is geodesic equation. You do not see any spin there. So it means that the spin now is in the coupling term here. The spin actually can change the equation of motion of the so-called center of mass. Now the other one is the spin. The spin, now you have another equation and also coupled this. Now this one basically is a definition of formalism. So all this. Now of course, since we know that, we can identify this one is without the spin, so we can artificially put a parameter here to switch off, rather than switch off the spin, rather than you just switch off the induction. So actually, we can investigate how big is the induction, what is the effect. So there's the system we have now. We also need to set a criteria: is the molar radius of neutron star is this neutron star is larger than the orbital separation larger than molar radius of neutron star. So this one guarantee that we can define the mass of the system, so we still treat it as a point mass. So first of all, let's look at the result. So we find all this kind of funny thing. So, well, okay, if you use a very simple description for layperson. So it means that cannot maintain a circular orbit. So then you say, okay, so what? But the other thing is, it's very, very sensitive to the mass of the black hole and the spin of the black hole. So what it means is that now we actually can measure the spin and the mass of the black hole, but just look at the movement of this. So if it is a pulsar, it's relatively easy. You see the number shift of the signal, then you get it. Then the question is, okay, can we do this? Is the signal big enough? So now, we look at, the vertical movement of that in the Z direction. So you look at, how big is that? Actually, the change is about 10 kilometers. So 10 kilometers translate into the light time is 30 microseconds. So if you ask, the pulsar timing people, 30 microseconds, no problem. They can easily deal with it. Now, so this is, that means, actually, it's usable. If you can identify something, if you can find it's usable. It is not something like, even though you identify it, it's impossible to do it. You have to do another LIGO or something like that. Not this. Secondly, there is another one is the per-resonance advancement. Now, so this one is also is relatively easy to do. So with spin coupling, you find that there's the top one is without spin coupling. This means the advancement. Now it depends on the spin. So the one you are familiar with in the sports and magic, if it's per black hole, then it can depend on the orbit is retrograde or prograde. So if you put in the spin coupling, now you find that the whole thing actually is completely different. So this one is the difference to this one. So what is the difference? It is of the order of 1 part in 10,000. So it's doable. So, and also, there is the drift in the time velocity component. So there's now the more interesting thing is that when you look at the the spin. If you look at the spin, I mean, the pulsar wobble. So it means that sometimes the pulsar actually will be inside, sometimes it's not. So occasionally you will see the missing pulse. Now, missing pulse, I mean, is very, very good compared to the continuous pulse. That means that the whole thing becomes digital. You just count the pulse rather than, I mean, you truly track the whole thing. So that is it open up a different way to analyze, utilize, I mean, the pulsar signal. So now, of course, I mean, this system is intrinsically chaotic. So sometimes, I mean, when it is in the chaotic situation, well, okay, then I mean, the nature is against us. But on hand, I mean, we see things that is very interesting. At least, I mean, we know this kind of system. But the question is, I mean, can we measure the difference? Actually, yes. Now imagine, I mean, the whole thing actually moving around in this toroidal torus area. This, I mean, is what we expect to see. We see, I mean, in different locations, you have the redshift and the blueshift. Now, this one is completely independent of frequency. It means that no matter what frequency you measure, that, I mean, you find the frequency shift. Like, for example, if the pulse are moving, I mean, towards us in this direction, then we see the blueshift and the redshift. And here you also see, I mean, the redshift, because, I mean, you need to move up. And also we get another one is the signal come after this. So it means that we get, if it is strong enough, actually we get multiple signals of this as well. Now this, I mean, this talk is easy, but in working is not necessary. So I show you an example. So what I just say is a frequency independent pressure. Now, so that one is the general relativity. General relativity tells us that, okay, when something moves from the gravitational well, we have the time dilation. So what it means that, I mean, the so-called frequency shift is about the time dilation factor. So if no matter, I mean, what frequency we have the same time dilation factor. So that is a general relativity. On hand, you put a plasma envelope, so if there is something there, then you find, I mean, something is very weird. So if the object means now, so let's say when you send a beam here with, I mean, different frequency, you find, I mean, actually different frequency actually coming out differently. So this one actually is a combination of the plasma effect and also general relativity. Now it is not separable. So you cannot say that, I mean, okay, now you have this, and then, but actually it's not. This one, I mean, when you look at the Hamiltonian, then you find that, I mean, there is a frequency dependent term, and when you solve, I mean, the equation of motion, you need to take into account of the whole Hamiltonian to do it. So this, I mean, is my student Tom Kimson actually did this. And so what it means that, I mean, when you do a pulsar observation, you put a telescope here, the pulsar, I mean, send a pulse and bend around the black hole. In some frequency, you can see it. In some frequency, you do not. But you move, I mean, the other position, you pick up the other frequency, not the curve. So there's. So now for the elliptical system, we got other things because things can repeat. But the hyperbolic system actually is more important because we can test the nature of time. The elliptical system basically time, I mean, just go around and around and around. For the scattering system, we have something called before and after. So before and after is important because now we can see whether we can switch the order. So if there's no spin interaction, the whole thing actually is the same. We are not talking about quantum physics or statistical mechanics. If you reverse anything in Newtonian physics, time actually does not matter. Similarly, I mean, in black hole, if you do not run into the inerrancy of the black hole in general, if the black hole is not spinning in general, I mean, the whole thing actually time reversal. So this, I mean, is the scattering. First of all, you found that, I mean, actually you can scatter out the thing. So it means that, I mean, the so-called Capellian description is no longer applicable. So this, I mean, is the thing. Now the other thing is, I mean, you also, I mean, find that, I mean, the spin-curvature coupling, of course, I mean, the spin, the change of the object. Now this one actually you can make sense of it quite easily in a classical analog. So because the spin interaction that allows so-called angular momentum exchange through the spin interaction. So if you allow angular momentum exchange, then there is no guarantee the initial angular momentum of the test particle and the final angular spin angular momentum of the test particle is the same because it interacts with the so-called orbit, even though it's hyperbolic orbit. Okay. So then, I mean, this kind of system is particularly useful to look at the self force. Now, self force, I mean, is a very strange thing. Not necessarily the high order, the force, I mean, becomes smaller. So I just use a illustration. So this one means the second problem in Gaussian order correction for the self force, and then use the second order is -3, the third order is -2. So the third order is stronger. Now, saying so, but we look at the system that we are looking at. If we take the mass of 10 to the 6 solar mass, is similar to the black hole mass of the Milky Way. And this one at 100 kilometers per second is the dynamical range of the system movement in the galactic halo. So in this case, we are relatively okay because the whole thing is 10 to the minus 8 radian. So it means that in one cycle or something that it is unless their effect is one part in 100 million, then we do not need to concern too much. So it means that we can use the approximation, what we did, and then we do the correction afterwards. So finally, we get into the gravitational effect. Then the question is, what is it? So it's a very strange thing. So if you have a, So if you have a curved black hole, now you have a test point mass. Now we're gonna, it's spinning or not spinning. So let's say it's not spinning. So we found that the period of prograde and retrograde orbit measured by the observer in this actually different. So it means that if this thing move from here back to here, and my computer go crazy. And that means the other way around, because the spin of the black hole can define a direction of rotation. So we found that actually is fixed. So this one, of course, it depends on the incarnation or all this kind of thing. So now let's simplify in the circular orbit. What do we get? So I do some exercise. It turns out that the whole thing is very simple. So you do it in a circular orbit. And it just depends on two things. One is is the reduced black hole spin parameter. It means how fast the black hole spin. The other one is the time crossing of the Pulsar radius of the black hole, which is the mass of the black hole. So it depends on two black hole parameters. You look at here, the angular momentum of the black hole and the mass of the black hole. So I put a C here because when I do the calculation in general, I use actually C is not. So then you look at that, the circle, the distance, the black hole is not there. So if it is not there, then, and also before that, we look at that, what is the time scale to do this? Now, if it is 10 to the 3 solar mass, it is millisecond. Okay, if it 10 to the 6 solar mass, it's huge. And the important thing is it's independent of the distance of the black hole. And so this thing is topological in nature. So yeah, not so surprising when you see a lot of things. Like for example, when we learn complex variable, when you integrate them around a pole, then you get the 2 pi I type thing. And also you do the parallel transport here, then you also get something independent of distance. So this thing is one of the things that generate to be independent of distance. So then the question is, well, can we observe this? Now, according to here, it's possible. But the point is, how do you make a neutron star move around and then suddenly change direction? So that not so easy. But before that, let's look at this. What does this term mean? So let's do a decomposition, linear decomposition. Now let's use the gravitoelectromagnetic representation. So we can break down the whole thing into the electric term and the magnetic term. Now the electric term is always at the plus. The magnetic term is always at the plus or minus. It depends on the direction. So the whole thing, the normalization is the Capellan motion. Now I put this one in red because this one is always redshift. So the electric term basically is like, if you look at that, it's RS Pulsar radius, depending on the orbital radius. Okay. And what it means is, this term actually is radius dependent. But the difference between the two terms, they cancel out. Okay. Now this one is a gravitational ratio. It's similar when you take the leading order of the Pulsar energy, it's RS divided by R. So the gravitational ratio. Now the magnetic term is more interesting. So it had the LS coupling term. So this one, actually it depends on the Pulsar equation term and the spin of the black hole. And this one is the LS coupling. So it means that the leading order is LS coupling. Now that is a good thing. It means that now we can use our machinery of Siemens splitting and Stern-Gerling effect. In fact, it's true. It is a generalized Stern-Gerling effect. So you write in a Hamiltonian form, So without the spin coupling, this is the standard Hamiltonian in general relativity geodesy. When you put in the coupling, now you have the dot term. So you have if you have two neutron stars, then you have the spin of the neutron star, you have the orbital motion of the neutron star, and the orbital motion of that, and each of that causes splitting. So it means that we have different combinations. So when we have a combination of this Hamiltonian, now it becomes a good list. If we cannot flip the neutron star, we flip the orbit of the neutron star. So there's actually we show it's doable. So there's my student K, quickly did a calculation for me a few years ago. So actually we can flip this. If we flip this, it means that now we can have a different combination of this, and then we can sort out the gravitational probability of the combination of this. So I think this is my talk, and these are the series of paper most closely with this talk. Start from 2013 with Graham as my summer student. So he was an undergraduate student at that time, and then he completed his work when he was a PhD student in CITA. And now he's a very established researcher in activity. And myself, in the last paper, it just got accepted. So this one, the time effect, I talk a lot of things. And there will be a following up paper K and I will write for analyze of the clock effect and the possibility to use hierarchy triple or just use the Pulsar and the neutron star to do it. Okay. Thank you very much. So this is it.
Thank you very much, Professor Wu, and let's give Professor Kinwah Wu a round of applause virtually. Yeah, we always do the virtual hand clap. Yes, and thank you so much for interesting talk. It really talks about GL is not quite as what we often feel, very highly precise, and the concept of time, the mass, how is it defined? Yeah, that raises lots of interesting questions. The floor is now open for any questions from our audiences across. So anyone have any specific question? If not, can I ask one? Professor, you mentioned about there's before the launch of LISA, we have to understand the self-force state. Can you explain a bit more on the how the LISA, what are they measuring, and therefore why self-force is important? Because I think we have a very broad audience here. Some of them may not know LISA that well, or may not know GR that well.
LISA is a space-based gravitational observatory. So it is similar to LIGO, but the frequency is different. It's a longer time scale system. So usually LISA, the scientific goal is the bigger mass black hole because the time scale is large. But in gravitational wave experiment is different from optical observation. Optical observation basically means you say, okay, I put the telescope there, and then I look at what I get. So if I get a structure, nice. If I get a structure, if I get a time. But for gravitational wave measurement, you need to provide a model, the fitting the template. So you're just sliding the templates to do. So if you are unable to provide accurate template, so if the template is not good enough, if you have the self-force, you will have drift. So you lost track of that. You cannot pick up the signal. So if I use not so funny type analogy. So if you say, okay, you want to put a forest and you want to find an animal or something like this for whatever reason. So you need to have a picture of the animal so that you can tell people that I'm looking for that animal. So but if your picture is not good or the picture has defect, there's some variation of that. So you ask the person to look at that, so the person say, okay, we can find the animal. But actually, the animal is that, but you do not see the mutation or whatever in that because you do not get a template. The self-force is, if the self-force is there, so it means that we cannot get a template of that accurately. So that means that we have problem to identify some group of source when the self-force is important. So one of the sources that particularly important actually is the extreme mass ratio system and intermediate mass ratio system. So that's the reason that in the LISA consortium, it is one of the sort of high priority goal to solve the self-force. But to do this is not easy. and we hindered by our understanding of general relativity, and also sometimes it is our mathematical capability. But with the pulsar is there, now it becomes important, because I mean, pulsar is not gravitational wave, and you do not need the template. So if we can lock the pulsar, we always have to know how the orbital dynamic change from the pulsar, and then we can do a good job to correct them in the templates according to the pulsar behavior. But the problem is, I mean, of course, I mean, is whether we can identify this system. So this one may depend on a lot.
Yes, I see. Thank you so much for explaining. I saw Xinyu raising his hand. Xinyu, go ahead.
Yeah, hi, Professor Wu. Thanks for the talk. Yeah, I have a very naive question. Hope you won't mind. Yeah, so in all your calculation of all this, let's say you get a spin coupling, spin orbit, spin curvature coupling for the pulsar, rotating pulsar. I'm wondering how important it is here there must be a neutron star. Suppose I have some gas or ionized gas just orbiting around. Would it also be show this kind of structure?
Unless, I mean, the gas, I mean, of the neutron star is much heavier than the neutron star. So this one, I mean, basically is independent. So you just put the key thing in the calculation. Basically, it's the mass ratio between the neutron star and the black hole. It is not the mass of the neutron star.
Yeah, let's say, suppose I have just the accretion disk, right? As a gas, ionized gas orbiting around this rotating black hole. How would you envisage any kind of?
Oh, that I mean is, I mean, there's what Tomkinson do.
So just the Bardeen-Peterson alignment, or?
No. The whole thing is, I mean, it depends on how clean it is. Now, to be honest, this one I may actually ask by the referee, I mean, of my paper. So the referee say that, okay, he say, I mean, lots of the black hole have accretion disk or something. At this point, if the accretion disk has the drag force, then I mean, you get into trouble. So I told him that, I mean, that is an observational bias. You look at the AGN to black hole ratio, actually it's a very small. And secondly, we are looking at the 10 to the 6 solar mass system. So these are the jaws for the galaxies. So what I mean is that, I mean, they are not easy to hold the gas. If you have a black hole accretion, you need to supply of gas. So it's a star forming galaxy or the big galaxy, you can trap the gas. Even, I mean, our Milky Way, the mass is quite huge. But if you look at, I mean, whether we have a strong accretion disk, no. In a small galaxy, if you are next to a big galaxy, the X-ray halo of the galaxy is strong enough to bait out all the gas. So it means, I mean, in the jaws of the galaxy, most of them actually is gas-free. Gravity tests are almost in gas-free.
No, but I'm more interested in, say, suppose you have all these various dynamics, how would you change the picture or understanding of the accretion disk structure?
Well, the first one, I mean, this one is related to the drag force. To me, I mean, this is not fundamental GR. Now, of course, if you are interested to do this, yes, you can do it. And secondly, this thing is interesting to many people, but for me, I'm not interested in the accretion disk affect the spin of the neutron star. I'm rather interested in how the spin of the neutron star interact with the curvature of space-time cleanly.
Okay, thanks.
Are there any other questions? Please feel free to raise your hand or put it in the chat. And meanwhile, can I also chime in another question for Professor Kinwah, please? You also mentioned about the gravitational wave memory, and could you kind of explain a bit more?
Okay, so this, I mean, is an interesting subject. So gravitational wave, after it passes through space-time, then it will change the space-time forever. So that's the main why I say memory. So you look at, I mean, if you, I mean, memory, it means, I mean, you reverse the time, it is different. And you remember at which particular moment it occurred. So that's why, I mean, we call it memory. So whether, I mean, any wave can cause memory effect, yes, we actually experience in optics. So what we learn, I mean, in ENM or something, you take the Maxwell equation. Of course, I mean, you reverse the time and you always get the same thing. But on hand, I mean, if you are optical physicist, you say, I mean, you pass, I mean, the pulse into optical fiber, and then the pulse actually change the electromagnetic property of the fiber. So it means that the second one to pass through that, it know that they are different. So graduation rate is the same. So now what is the effect of this? So now let's say, okay, LIGO continue to receive signal. So it means every time the graduation rate pass through LIGO, it changes the length of the LIGO. But how come we do not do it? Because LIGO is mounted on the ground. So the amount on the ground, it is not free fall. So it means that eventually you readjust the whole thing. But this is different, from laser. Laser is a free fall in space. So if you take gravitational wave pass through laser, it changes the separation of laser. So it means that people need to recalibrate this. So when laser finishes its lifetime, then it can record how much change it is. Then it will pick up the memory from the gravitational wave. So it means that when these die, that also means a very, very important information that we can get to understand the meaning of. And gravitational memory, had a different component, if you say. Then each one is different. So this, still one of the areas that people are looking at. So this is important to do this because it's a free fall.
Yes, thanks so much, Professor. What order of magnitude of differences are we considering here?
Now, if you look at go back and do this. So this one, so, oops, I need to use share screen. So how come?
Please try now.
So I need to go back to screen. Yeah. Because my pointer cannot move to the share screen. Do you lock the screen? Or
no, I haven't. But let me try again.
Okay, now I
can you?
Okay, now I can do it. So I need to find my share. You see my screen now?
Yes, yes.
Now, so this system, actually, you put a Goblet cluster 5 kiloparsec away. So now, you can see it being the maximum of the string. And now this one is a good fraction of the string. So that is relatively huge if the system is close enough.
Yes, and the order of magnitude on the y-axis, we are looking at 10 to the power minus 18 and minus 20.
So that's again the gravitational string.
Oh, okay, that's okay.
So that one is small. It's not one part of it. That is the string. You need to compare with the pulse. You need to compare with the maximum pulse. Rather than they take the absolute value. The system farther away, this one smaller, this one also smaller.
Okay, thanks. It's very interesting to know when a mission approaching the end of life, actually we can learn other physics.
Well, even before it is end, actually you can collect a lot of information. But when it is end, the whole thing becomes a done deal. Yeah.
That's a very, very interesting thing to think about and consider. And it's a very interesting talk with lots of equation. Citizens love equation, but I think we also take some time to digest what you said. Thank you so much, because we also, the part of the SSSS series is also to really think about when we come to observation, how we can use theory to drive our understanding and making those connections. And from today's talk, you really point out some of the things, at least it's off my radar. I never come to notice. It's like, oh, wow.
Yes,
so
it's good to see some of my students here. Senior is my student, was my student, Dennis and Ashley as well. So, of course, we.
Yes. And this is approaching the 4 hours. Some of us already have to go sharp for the next meeting, but let's give Professor Kinwah another round of applause to thank him for such an interesting and great talk.
Okay, thank you very much.
Thank you so much.
I will hang around here for something or something. Yeah, I will hang around here.
Yeah, cool. Thank you so much. And I will stop the recording.